Uh, I think without spending much time, let's move to the next speaker of the session, and that's going to be Anusha Kadimisetti. She's also from Frontier Lab. She holds a biotechnology degree with over 7 years of experience in business development, marketing, and R&D, especially in pyrolysis GCMS systems for diverse applications and polymer characterization. So she also has expertise across multiple domains, including pyrolysis, material characterization, technical marketing, project management, and biotechnology. So, let me welcome Anusha to give the next lecture, and that's going to be more related to some specific applications of analytical pyrolysis GC mass spec. Over to you, Anusha.
Thank you, Venusan. Thanks for the intro. I hope I'm audible.
Yes.
Yeah. So without any further delay, I'd like to start my today's presentation. Oh, is the screen visible?
Yes. Yeah.
Okay. Good morning, everyone. Today I'm going to talk about the PYGCMS use in failure analysis of advanced polymeric materials. So as already the intro is given, currently I'm working as a business development manager, taking care of the technical marketing activities in India, behalf of the headquarters. So in the further, in talk of today, I'm going to cover about the objective, the background studies, and also the introduction configuration of PYGCMS, followed by the workflow, giving the example with 2 case studies, and finally the results and conclusion. So this is our headquarters. I think in the previous presentation, Michaelson already given the beautiful intro about our team, our company, foundation, founders, and everything. So let me quickly jump into the first case study. So this is about the pump diaphragm with a limited lifespan. So we have received a sample from the customer who is actually facing failure in the diaphragm of air pump, and they don't know the reason, and what kind of failure they see is there is some kind of cracks appearing in the air pump after a certain period of time, whereas the good diaphragm is working like more than 1200 hours, whereas the defective one what we are going to address is like showing the crack between less than 800 hours. So the reason is not known, and we don't know what are the differences we do see in between these polymers. So to address this issue, what we have done is we simply took the piece of this diaphragm and then we introduced into our PYGC MS system, and then we further carried on our studies. Uh, in the previous slide, Michaelson explained more detailed way of tools and what kind of tools are involved in sampling. I just want to quickly give out a short intro. Since this is like a rubber or kind of solid materials which are soft, we usually use a knife to cut a desired amount of the sample and introduce into the sample echo cup. And also if it is a hard pellet, what we do is we take the prepper. These are all tools available in the sampling toolkit of the Frontier. So what we do is we just grind using rub using this polymer prepper, and then we take the sample, and if it's a liquid we use a micro syringe, and if it is sheet kind of thing or fabrics, what we use, we take a simple micro puncher and then we take the sample. Thereby we weigh the desired amount of sample. What we usually suggest is zero point 0.5 is 50 microgram is far more enough to do your analysis, and we weigh it into the echo cup, and thereby we introduce into the pyrolyzer. So even this talk is already covered by Michael San. I don't think so. I need to again, go deep dive. So I'll just quickly show you. This is how the echo cup drops into the quartz chamber, where it has the ceramic heater, where the pyrolysis happens, and thereby the volatiles flush to the GC column and then to the MS detector. So all these instruments coupled with the PYGCMS are detailedly explained by Michael San in the previous talk. So when I talk about analysis, or when I talk about data analysis or sample analysis, the techniques what we follow is EGA. Thereby, then we drew the method map, like, either it can be thermal desorption or hard cut or the pyrolysis, or further, for complex samples, what we do is the reactive pyrolysis. So by this slide, I would like to explain one thing, that whatever the sample might be, like, we always suggest you to go for EGA first. Thereby, it helps us to address the sample in better way, and also how to deal the sample in terms of, the temperature zones. So it cuts down the hassle to, analyze the entire sample, and it gives us a better focus in viewing the sample with a particular interest of our product. So here what we have performed is, first we have taken the sample and we have carried out the evolved gas analysis, nothing but the EGA, very similar to TGA, but whereas we get even the mass spectrum data here. So this is the first slide showing the EGA, the thermogram of the rubber samples. So here we could see that the peak apex is somewhat slight difference, very slight difference. Whereas in the good sample, we could see the peak apex is appearing at 490 and the bad sample is at 498. Apart from that, we could see between 200 and 400, we could see two peaks appearing here. And the small peak is coming at 335 degrees in the good sample, whereas it is not present in the bad sample. So this gives us only the simple thermogram idea, but it will not give us the overall view of what is involved in the sample. So to know better, we take this as the evidence to, to perform our first study. So from this EGA, we have found out that, the major concentrated zones is between 200 to 400. Thereby, what we have did is we have done the EIC. It's nothing but the extracted ion profiles obtained from the EGA curves from both good and defective samples. So we have seen that M over Z of 73 and 129 at 355 is clearly visible in the 335 at the 335 degrees peak, whereas you can see the common peaks appearing between, 55 and 57 m over Z at 269 might be the characteristic ions for hydrocarbons such as oils and all. So even this will not give us the entire idea of what is wrong with the sample. So to know better, what we have did is we have quickly performed a simple single shot analysis at 600 degrees, and what we have observed here is, you could see in the small yellow boxes here, the good and the bad samples, where two peaks are detected only from the good sample, whereas in the defective sample they are not detected. On the other hand, the hydrocarbons which are detected around 18 to 22 minutes are detected more from defective sample than good sample. So by this, we have found out that there are two major peaks appearing in the good sample. So to know what these peaks are, we have quickly performed the F-search using our F-search software system, and thereby we found out that the peak one, what I'm talking about, is nothing but the 1-chloro-4,1-chloroethyl cyclohexene is nothing but from the CR, that means chloropin rubber, and the peak 2 is the palmitic acid. So what we have did is, yes, in the previous slide I have showed you the evidence that it is from the chlorophene rubber, and you could see even the percentage is like 97% matching. But to make it more evident, what we have did it is nothing but we have compared the MORZ 88 of the chlorophene rubber with good and defective sample, and we found out that both monomer and dimer are detected in good sample, whereas in defective sample it is not present. Thereby what we have did is we have quickly performed a hard cut analysis using the an accessory, as Michelson already pointed out in his previous talk. So here we have considered the zones, and we have fragmented into three zones, like zone A, zone B, and zone C. Here we have did it. So in this method what happens is the vapors evolving from each zone are selectively introduced into the GC separation column, and thereby using the device called selective sampler in the previous talk, as Michelson has mentioned, this is mainly useful for performing the hard cut analysis. And thereby we have also coupled with the microset cryo trap, and we can fragment up to 8 thermal zones, but here we have only fragmented to 3, and then we performed a hard cut analysis. So zone A is between 200 to 300, zone B is between 320 to 350, and zone C is between 460 to 520. Let us see what's the output of this hard cut. So here are the chromatograms that we obtained from the hard cut analysis. You can clearly see that in zone a peak, we have labeled the peaks A, B, and in zone a special peak called C is appearing here, whereas in the defective sample it is not there. As well as in zone B, you could see peaks called E and F are appearing, whereas in defective samples they are not present. And zone C is slightly different, but moreover the same. So here we can clearly see that three different peaks are detected from the good samples, nothing but C, E, and F. Let us see what they are. So to know what they are, we have quickly carried out the library search using the F search as I've previously shown, and we found out that the zone C is nothing, so the peak C is nothing but a plasticizer called DOIP, and peak E is palmitic acid and peak F is stearic acid. So they are nothing but some tenderizers and all. So thereby we concluded that okay, the composition of the polymer is different between good and defective sample. So what is the difference is nothing but some additives, especially like a plasticizer and at some tenderizers are contained only in good sample. So that means the palmitic acid, as I've shown, also the stearic acid and DOIP, the main compound from CR are already, are there in the good sample, whereas they are absent in the defective sample. So this is the reason why the diaphragm is, limited lifespan is showing in the defective rubber, whereas compared to the good one. So let me go to the next case. In the second case, I'm going to talk about the analysis of the white turbidity of PVA by using the PYGCMS technique. So in this case, what we have received is we have received the PVA from the client, where their issue is nothing but they could see some kind of turbidity during the production process. So even they were not aware of what is causing this turbidity. So to address this problem, you can simply say that why don't you, filtrate and use the techniques like NMR and IR and all, but it is very difficult to do the filtration because it's already turbid. So the contaminated product is, might be because of the impurities or whatever reason. So the turbidity occurred and we cannot filtrate that easily. And also at the same time, for NMR and IR, the pre-treatments are need to be done, which are like little hassle, whereas the PYGCMS is like very simple technique where no cumbersome pretreatment is required. Simply introduce your sample to the echo cup and then perform your PYGCMS analysis. So here to address this problem, we have quickly taken the desired amount of sample and introduced this both qualified product and also the turbid product to our PYGCMS system. And as I talk about, initially we always do the EGA, whatever the sample is known or unknown, we always recommend you to do the EGA. So this is the EGA data. What we have seen is like in the standard and the turbid PVA, the the thermogram is showing a very slight difference in the EGA curve, whereas the average mass spectra do not provide much clue, um, what is causing this impurities and all. So only with the evidence of EGA we cannot conclude anything, but we can address the problem in a particular direction. That means it point out to which direction we need to focus. So as we could see here, maybe these zones are slightly different, and also even the peak apex is also slightly different. What we have done is we have simply done the first single shot analysis to know better, and here you could see the peaks are somewhat same, just only the peak intensity is what you see is varying, like slightly difference in the peak intensity. So even by performing this simple single shot has not given us the clear cut idea of what is causing the turbidity. So to know better, what we have done is we have done the hard cut analysis. Here we are focused, our main focus is on this zone, as I've already shown you. This is where the difference is seen. So what we have did is quickly introduce that zone, and between 460 to 540 we eluted a data of the chromatogram, and this is what we observed. You could see here, like from here to here, like a series of peaks are being appearing in the turbid PVDA, whereas in the standard PV, like there is no much peaks appearing, like series of peaks appearing in the standard PVA. So to know further, what we have did is we have did a simple selective ion monitoring mode, that we call it as SIM mode, using the M over Z ion of 57. And here we found out that you could clearly see that alignment of hydrocarbon appearing in the turbid PVA, whereas in standard PVA there is nothing. So this means the turbid PVA is containing some kind of hydrocarbons which are coming from some particular compound. We don't know what is that, but to know that, what we have done is we have taken the standard MOZ ion 57, and then we have ran the EVA, and we found out that the turbid PVA, whatever the series of peaks appearing in the turbid PVA, are nothing but very similar to the pattern that you see in the standard EVA. So the peak pattern of these saturated hydrocarbons are pretty similar that we have seen in the turbid PVA. So by this we have concluded that okay, so the EVA, that means the ethylene vinyl acetate copolymer, which is used in the production site, might be, or like it is considered to be the cause of turbidity of the product. So the summary is nothing but, so for this kind of failure analysis, or for this kind of products where we could see an occurrence of defect or turbidity or impurities or whatever it might be, using this kind of techniques like hard cut coupled with GCMS and also EGA, all these things, we have found out that the polymer having a saturated hydrocarbon structures that are appearing from the EVA. So mainly uh, the cause for the turbidity. So this EVA can be used for cleaning process and all. Maybe the production site earlier used by someone and then shifted to the next customer, where they started the PVA production, and then they have seen this EVA, occurring. or interfering between the production process of PVA and causing the turbidity. So this is the reason for the turbidity of the product. Thereby, I conclude my talk. I hope I have covered both, case studies. So all I want to say is for this kind of industrial failure analysis, or for reverse engineering, this kind of techniques like, uh, coupled with the simple GCMS can be a very rapid tool for characterization and for addressing this kind of problems. Thank you.
Thank you very much, Anusha, for giving a very detailed insight on the application, especially the failure analysis using PYGCMS. Uh, I think it's a very good insight about finding even a minute, practical, issue that could really cause any failure.